Hello folks, today I'm going to be finishing with the rotational kinematics. Before we talked about angular variables in rotational kinematics. We talked about angular velocity, angular acceleration, and angular distance traveled. We talked about how the equations for these values to be found are similar to the linear kinematics, and we saw some problems in the course, in the class. Today I'll be talking about tangential variables, solving some problems involving tangential variables. One of the questions we solved in the course and during the learning catalyst session was actually using tangential variables already because we know them from uniform circular motion. So I'm going to be identifying them, re-identifying them as variables, and also some problems. As we all know, when we have a circular motion, we talked about angular variables. Let me leave them here now and talk about the tangential variables. We talked about the tangential speeds. We were calling them V. So far, it's the speed traveled along the circular path. I'm going to call it Vt now. Due to a reason, I'm going to talk about another type of velocity that is equal to this, which we will call a linear velocity. This is also linear velocity, but we'll get there. So Vt is tangential velocity. Now, we have still r, omega is still here, circular motion. Now, though, each of these velocities are varying. We talked about alpha, angular acceleration. Now, our tangential speed is also varying, and we have an acceleration along with what we will call tangential acceleration. And if the object is accelerating, it will be along with the same direction. We will call this AT. And if the object is decelerating, the deceleration of a circular motion is also possible. We learned for the angular values already. For the tangential values, it's the same. Deceleration is also possible, and we can show the direction of acceleration. And if an object is decelerating, it will be negative. In the center panel, acceleration is still here, so we'll have AC. And as you can see in here, we have three types of acceleration. We have angular acceleration, we have centripetal acceleration still there because we have circular motion. This is the acceleration, maintaining the change of direction of the tangential speed. And now we have another variable involved, tangential acceleration. While the direction of the tangential velocity is changing, value of it is also changing, where we need two types of accelerations. So the tangential speed is defined the same. The distance traveled in certain time along the circular path, the same as the circular motion. So let's draw this again and show this only in here. Now we're going to separately talk about all of these tangential variables. So we have r, we have tangential velocity, and again the tangential velocity is described as the arc length traveled along the circular path during a certain amount of time, or during unit time. If I call this arc length traveled, let me not put an arrow in here, s, or delta s, right? Let's call this delta s. And the time it takes for this travel is delta t. Average angular tangential velocity. So we're looking at here one tangential velocity. So we're looking at tangential velocity among these tangential variables we talked about. So the arc length is traveled per unit time. So average value of tangential velocity will be here, delta s over delta t. Again, we're going to drop this average value later on, but that's what it is. Average tangential velocity. And the unit is meters per second. As always, the distance will be in meters and time will be in seconds. And similarly, instantaneous tangential velocity, Vt, will be s over t. Distance traveled divided by the time. And often we have the interchanges values. We will be using this value because the instantaneous velocity will be equal to average velocity most of the time. Unit is the same. In the beginning, we learned that S is equal to theta times R, or theta is equal to S arc length over R. Replacing this in here, the tangential velocity can be expressed as, let me draw another, as instead of S, we put theta R, theta times R over T. And the distance, angular distance traveled per unit time was equal to omega. Replacing that in here, we're going to find the same equation as in the uniform circular motion. The tangential velocity is equal to angular velocity times r. This still holds in here. And this one is the equation we already used in a question. If we know the angular velocity and radius, we can get to tangential velocity directly. If we don't know these and we know the arc length traveled and the time, we can also find it from S over T. Unit again is meters per second. So this is tangential velocity. Let me see what else. And that's pretty much it. Average value delta S over delta T and instantaneous value S over T. I'm going to delete this and I'm going to talk about tangential acceleration. So tangential acceleration. We'll call this AT. It is this acceleration that is parallel to the tangential velocity in the same direction if the object is accelerating, opposite direction if the object is accelerating. And it's the change of tangential velocity per unit time. The same description as the acceleration we defined before. So average tangential acceleration will be delta V tangential over delta T. Acceleration. And instantaneous tangential acceleration, of course, will be V tangential over time. This is instantaneous. Acceleration. And the unit, as always, is meters per second squared. Same in here. Now for the tangential velocity, what we can do is we know V tangential is equal to omega times r. And we can replace this in here and rederive an equation for AT tangential, replacing VT by omega r. Omega times r over t. And before in the angular values part, what we learned for angular acceleration is the change of angular velocity per unit time. So angular velocity divided by time was equal to angular acceleration. This is the way to find it. Replacing here this part by the angular acceleration, we're going to find a very useful equation for tangential acceleration. It's equal to alpha times r. So tangential acceleration is equal to alpha angular acceleration times the radius. The unit for alpha was rad per second squared, and r is meters. The unit for AT will be meters per second squared. As I've talked in the previous lecture, rad is just a number, not really a unit, so it just disappears in here. We are left at meters per second squared. When we are expressing the angular velocity, angular distance, and angular acceleration, though we use the unit as rad per second squared, but rad is like coming from expressing the angles in terms of pi's, and pi is the number, not actually a unit. So it disappears in here, and we solve for 80 units per second squared. Vice versa, if I know AT and R, I can solve for alpha, right, as AT over R. So there is very, very important two simple equations we can always get help to find values. Vt, tangential velocity, is equal to angular velocity times R, always holds, and the unit is meters per second for tangential velocity, rad per second for angular velocity, and meters for R. If I know two values, I can find the third one. If I know Vt and R, I can find omega. Or if I know omega and R, I can find Vt. Or if we know the angular velocity and tangential velocity, we can find the radius of the circular motion. And here it's very similar. Tangential acceleration is equal to angular acceleration times R. And we can find values depending on which one we know. If we know two of these, third one can easily be found. So we now have two new variables. Tangential velocity, which is not really new, but it's only varying now. That's the difference from the uniform circular motion. And we have now tangential acceleration, because if there is any velocity varying, the variation of velocity per unit time is the acceleration. If the tangential velocity is varying, then we have tangential acceleration. Now what we are left with only is centripetal acceleration. We already know that thing from uniform circular motion. It is found exactly the same way as before. So the third value, this will be centripetal acceleration. Maybe it's redundant, but I want to remind you again what AC was. So again, the acceleration towards the center of a circular motion, the circular path of a motion, and it is the reason for centripetal force. Centripetal force was equal to MAC, if you can remember from uniform circular motion. It's still there, now it's only varying. Because centripetal acceleration, let me draw this in here separately. I'm going to drop the velocity, I'm only going to draw centripetal acceleration. So here's R, we have a circular motion, and centripetal acceleration will always be towards the center, anywhere in this circle. Causing a force, it is always towards the center, Fc. As solving questions, we're taking Fc pushing outward, because that's how the object perceives it due to the moment of inertia, or the property of matter of inertia, like action-reaction forces, but it's actually towards the center. So we have AC toward the center always. If we know Vt or omega, I put everything again, we can solve for AC. And it will always be equal to omega squared times R, or V tangential squared over R, which was the case in uniform circular motion. What we will be seeing now, though, this AC will also be varying along the circle, because it's directly proportional to omega and Vt, and they're also varying along the circular motion. This is one thing. Another thing, if you're ever asked about, in these type of questions, we're not generally interested in the centripetal force, but if you're ever asked about centripetal force, it is always equal to MAC. Now AC will be varying, so centripetal force along the circle will also be varying. One of you have given a nice example of actually the roller coaster motion we were looking at. We assume that the roller coaster has constant velocity, maybe in some questions. We said this is uniform circular motion, but it's not actually uniform circular motion. If you are getting along a loop in a roller coaster, the velocities, angular and tangential velocities, are changing along this path. And thus the force, centripetal force applied to the object in a roller coaster car is also changing. One last thing now. Acceleration is a vector, And we have two types of linear acceleration here. We have centripetal acceleration and we have tangential acceleration. So we will have to find the total acceleration of this motion, the total linear acceleration. I'll just call it total acceleration. And let's name it A. We had AC, we had AT, so let's call it A. So we have centripetal acceleration. Let me draw another circle here. Okay. We have a non-uniform circular motion. We have R. We have a centripetal acceleration, AC, towards the center always. And we have now a new type of acceleration, AT, tangential acceleration. The total acceleration A is the vector sum of these two accelerations. So we will be adding these two vectors, taking into account that they are vectors. They have to be vectorially added, but one method of doing this is to draw a parallelogram in here, and the line joining the start of two vectors to the end of the parallelogram, drawing the diagonal of the parallelogram, it will be the total acceleration in here. And direction will be that, the one we see in here. To find the value of this acceleration, if you can see, we have a rectangle here. If we use the head to tail method, this will be carried in the top there, here. AC will be here. And to find a total, we can use Pythagorean theorem. Let me also show this to you. Now I'm moving into the magnitudes. A squared will be equal to AC squared plus AT squared. This is what Pythagorean theorem is, math review. So A, taking square root of both sides, will end up with A is equal to square root of AC squared plus AT squared. Right now I'm going to solve a question involving this. What you might also be asked in a question is to find the angle between the radial direction and the total acceleration, theta. This could be also a question involved in another problem. Radial direction is the direction along the radius. So theta angle can be found. Let me delete this part and write it down here. So theta here is the angle between A and R, or radial direction. And it can be found using tangent value. Theta is equal to tangent 2 minus 1. And tangent will be opposite or adjacent. Opposite would be equal to AT, so tangential divided by A centripetal. If you are not comfortable with how to find an angle using tangent, you can also use sine and cosine, but we generally use tangent. Go back and check the math review part, so you can just use it from anywhere involving trigonometric functions. Also, we quite often use this Pythagorean theorem when we're adding vectors, so this should be fine. I hope if you're not fine with that, go and review that part as well. This is it. This is the tangential variables we will have. Now let me write down the most important equations we will be using right under there, so we have everything we need to solve some problems. Okay. Don't want to use my small board too much, so now we have tangential variables. And most useful equations related to tangential variables, we have V tangential, let me put this below, V tangential is equal to omega times R. We will quite often use that. A tangential is equal to alpha times R. And A centripetal is still V tangential squared over R or omega r. So as we find the tangential variables, what we learned before finding about angular variables, in a question we can first find the angular variables and then jump down to tangential variables using these equations. Or depending on the question, sometimes the tangential variables are given and we can use these equations to jump to angular variables. And another thing we learned that the total acceleration will be square root of a tangential squared plus a centripetal squared. And let me also show you that angle between R and A, radial direction, and the total acceleration is equal to tangent to -1. This is not an equation, this is just a trigonometric fact. But let me also put this in here, AT over AC. Now, this is a linear kinematics along the circle actually. It would be very much fun to actually use the linear kinematics equation, just the same as we know before, to calculate VT possible using AT. You know, V0 is equal to V equal to V0 plus AT. Calculate the distance along the circle using x is equal to V0 T plus 1 to x AT squared and so on are all possible. But generally, we do not need them. These simple equations gives us the same results. So we'll be using these generally. And let's solve an example question in here. Let me find my question involving tangential and centripetal acceleration and total acceleration. Every values, every equations we know from uniform circular motion is also applicable in here. For example, if we know, let me also remind you that as well. If we know period and frequency, if there's a motion that has a certain period and frequency, we can again calculate omega angular velocity is equal to 2 pi f or 2 pi over t. This still holds. And V tangential will be 2 pi fr or 2 pi r over t. Coming from omega r, let me leave this here for a while as well. I don't think we'll be using them in today's questions, but they're all usable if there's a motion that is non-uniform, circular motion, but it has a certain period and frequency, which is quite possible to happen in life. So let me try to draw what we have here. There's a person, discus thrower. I'm gonna say the words after I hopefully draw this. So this is the head of the person, and he is throwing a discus starting from here and accelerating it, coming it there, and then throwing it away from this position. At this position, better, so it will have the tangential acceleration and centripetal acceleration. Let me now read the question. So a discus thrower starting from rest. A discus thrower accelerates the discus to a final velocity of 15 rad per second. So we are given, so we're assuming there's a full circular motion in here and calculating what we need to calculate using uniform and non-uniform circular motion knowledge we have now. So omega final, what we always call omega, is given 15 rad per second. Omega initial is also given. Starting from rest means it does not have any velocity in the beginning. So initial velocity is 0. Both angular and linear actually are 0. One is 0. From here we know the other is also 0. During the 15 rads per second, a time of 0.27 seconds. So the time 0.27 seconds. He or she is throwing this discus, rotating it, and giving it a velocity, accelerating it in a certain time. We have both acceleration, ACAT, plus angular acceleration, alpha. Alpha is not also equal to 0, so we have an alpha, AT, and AC. We don't know them, but we can calculate them. During the acceleration, the discus moves on a circular arc of radius 0.81 meters. So the circular arc of radius, the radius that the discus rotated is equal to 0.81 meters. So during this flow, the discus moves along a radius in an arc that has a radius of 0.81 meters. Let's see now what they're asking. Find the magnitude of total acceleration. So A is asking us. Find the magnitude of total acceleration. A is asking us what is A. We're going to find AC, we're going to find AT, and add them up vectorially using Pythagorean theorem to find what A is. That's what we are looking for in part A. Now, I don't know AC, I don't know AT. First of all, I can find AC easily. I know omega, I know R, right? I can use this equation, which, by the way, should be omega squared R. So let's find AC first. AC is equal to omega squared R. Omega is 15 rad per second times R, 0.81 meters. And the value of this should be 182.25 meters per second squared. Now we have that. To find AT, what we can do is get alpha using all these values. Over here, I can use omega is equal to omega 0 plus alpha t to get to alpha. And then I can use alpha to get to AT simply using AT is equal to alpha times R. So let's do that. First, find alpha. Because if you find one and if you have R, you can find the other, AT and alpha. Find alpha using omega is equal to omega 0 plus alpha t. Omega 0 is 0, cancels. We know time, we know omega, so alpha will be equal to omega over t. Instantaneous acceleration, angular acceleration is also equal to that, coming from the same equation. So what is omega? Again, 15 rad per second divided by time, 0.27 seconds, and the answer should be, I'm not going to lose time on recalculating these, 55.56 or 55.6 rad per second squared. Now I have alpha, I can get to alpha t easily, sorry, AT easily using alpha R. Alpha times R will give me AT, and my alpha is 55.56 rad per second squared. Again, I like giving 2 decimal here. You can also give this 1 decimal. All acceptable, all perfectly correct. 0.6 times R, 0.81 meters. From here, AT should be 45 meters per second squared. 5.0 I have there. Please calculate and make sure that these calculations are correct. Also will be a good practice for you. Now I have AT and I have AC. I can easily find A. Let me draw them here separately. This is our AT and we know the value now. AT is equal to 45.0. And we have AC in this direction. Not very good, isn't it? Maybe. So we should have yes. We have AC is equal to 50, that here, 182.25. Both meters per second squared, and I am looking for their addition. I am using parallelogram method, and this is my A. And using the Pythagorean theorem, A is equal to square root of AT squared plus AC squared. The answer to total A should be 187.73 meters per second squared. Again, we use Pythagorean theorem to find A. Please check that as well to see if it's correct or not, and let me know if there's any error in that. I calculated some time ago. I didn't recheck the calculations, but it should be correct. Please practice and let me know. Now part B is asking us what is the direction. Let me read it actually. What is the angle a total acceleration makes with the radial direction? That's what B is asking us. What is the angle in between the radial direction, which is this, towards the central was along the radius, and acceleration, theta, which is the thing I have given in here. I want you to see it in here and understand it perfectly, that we have, let me draw it again, AT in here, we have AC, and our A is the vector addition, which will be this. Now I'm adding these two vectors using parallelogram method. If I use head-to-tail method, what I would do is to carry AC here, right, tail of AC to head of AT. This is also a review for vector addition, which we use quite often for forces in Newton's laws. And the vector connecting the tail of AT to head of AC is our total A. And this is, AC is always along the radial direction. Direction along radius. It's the centripetal acceleration. So when they ask us the angle A, total acceleration makes its radial direction, or the radius of the motion, is this angle. Here, this factor can be also carried down in here. This side is equal to AT. So let me draw this with red. And tangent, theta, is equal to opposite or adjacent. That's where it's coming from. This is also a trigonometry review. Tangent theta is equal to AT over AC. And to find theta from here, you can use this for sine and cosine and tangent and cotangent, all works. We say theta to minus 1, theta is equal to, tangent to minus 1, AT over AC. And what we find, we know AT and AC, which I forgot, I deleted already, let me find them from here. So our AT was 45, tangent to minus 1, 45 meters per second squared. I'm dropping the units, so let me not drop them. Meters per second squared divided by AC, 182.25 or 0.3 meters per second squared. From here, what I found for the angle is 13.9, around 14-degree angle. We find the angle from here as degree. And that should be the answer. Check the answer. It should be correct. I just checked it today. And that's it. Angular tangential variables are the most new ones are AT and AC. We already know the tangential velocity, only it is varying now. I want to talk about also rolling motion. It's been some time, but we'll finish in here, so not very long. It will take. We have this non-uniform circular motion in life a lot. I asked you to put some examples. We have yo-yos doing non-uniform circular motion. I'm not really talented on that, but some people are. So when you're playing with a yo-yo, what you have for yo-yo is non-uniform linear motion. We solved a question involving a fishing rod, the car drives, and they have also non-uniform circular motion. As the car accelerates, the tires rolls, and they have non-uniform circular motion. We bike, we have non-uniform circular motion. So a lot of things are involved in non-uniform circular motion. Centrifuges are also increase in speed, decrease in speed, all possible to change. So rolling motion has a slight difference, so I just want to touch it, not really something very new, but when you're driving a car, let me try to draw a car. start your motor and you give the car a linear velocity, and the tires start to rotate and you start moving. These tires will have a tangential velocity along the edges. Each point will have a tangential velocity. And what we find is that the linear velocity of the car, v, is always equal to tangential velocity along the edges of tires. Because if you look at one tire, let's say we start from here, point A, and it will roll. As it rolls, rotates, it will be traveling some distance here, right? And this is what the car is traveling. They generally call it D or X. Let's say take one revolution. After one revolution, this point A will rotate and come back to same position. So we'll have this in here, A will come back to same position. And the distance traveled after one revolution will be equal to 2 pi r. This is for the tire, and as the tire goes in this direction, rotates, this is the distance car travels. So the distance car travels in a unit in a certain time, let's say it's t, time is t, is equal to the point A travels around the tire, which is why we always have the linear velocity of the car is equal to tangential velocity of any point along the edges of tires, Vt. And that's all about it, simply. We can find Vt using these equations. As we know, Vt is equal to omega r. Once we find Vt, we have V. And if we ever see questions involving these values, that's what we're going to do to solve them. Anything else? Let me check. And then, it's been kind of long, but I have a long question here. Maybe I'll just solve first part of it and I'll ask you the rest. If we are also asked the acceleration of the car, we can also relate the acceleration of the car to tangential acceleration. I'm sure you can all see this now before I say it. If the tangential velocities are equal, the accelerations also will be equal. So the same way, the linear acceleration of the car will be equal to tangential acceleration of any point along this tire. And we know we can find tangential acceleration using alpha r. After we find tangential acceleration, we can go to linear acceleration. And we can calculate some stuff using that. Now, let me quickly touch this question and describe you how to solve the rest. I'm going to post these notes online, so you'll see the solutions there as well. And I'll let you go. One question involving these. So, example of rolling motion. An automobile starts from rest and for 20 seconds has a constant linear acceleration of 0.8 meters per second squared to the right. So there is a car. I'm stopping to see what I have in here. I have a car starting from rest, which gives me, let me take this pen. The initial velocity is 0 meters per second. And it starts accelerating the linear acceleration 0.8 meters per second squared. So we only know now linear acceleration and initial velocity for 20 seconds. So we have the time as well, 20 seconds. To the right. As it says to the right, the car is going in this direction. The tires will be rotating clockwise. General conventional use of directions as positive and negative in this circular motion is clockwise direction is negative. I told this in the previous lecture too, I believe. And counterclockwise is positive. So this direction is negative, this direction is positive. In most of the textbooks, the values involved in clockwise direction could be given as negatives. But I don't think this is necessary. As long as you know the clockwise or counterclockwise, you resolve the physical issue of directions. And we'll be just looking at the magnitudes. However, in some questions you might see the values we will find, for example, for theta, angular displacement will be given as negative in here in the books because the direction is clockwise. That's what the reasons only. But I'm not going to use it here. Just know where it's coming from and don't confuse yourself. So the car is going to the right, the tires are rotating clockwise, the direction of omega, theta will be, the rotation will be negative, and theta will be negative. The radius of the tires is 0.33 meters. So we also know the radius of the tires, 0.33 meters. Okay, I'll leave this kind of big one. Now there comes the question, at the end of 20 seconds interval A, what is the angle through which each wheel has rotated? So A is asking, at the end of 20 seconds interval, what is the angle each tire has rotated, which is the angular displacement? Yes, so for the angular displacement, this is the equation we look at, or this one we can use, but we know time, right? We kind of know omega 0 because we know V0, and we know omega is equal to, let's say V is equal to omega R, right? Vt and V are the same. So if this is 0, V0 is 0, omega 0 also should be 0. So V0 is omega 0 R. So if we know initial linear velocity to be 0, automatically we know initial angular velocity is also 0. Tangential velocity is also 0. So omega 0 is 0. In this equation we can replace it. We know T. If we can find alpha, we can get to the value of angular displacement. Now let's see what we have. We know A, linear acceleration, and we know this equation, linear acceleration is equal to tangential acceleration, which is equal to alpha times r. So we know A, we know r, we can get to alpha easily. Let's use that to get to alpha first. A is equal to alpha r. This is coming from the fact that A, linear acceleration, is equal to tangential acceleration. Because tangential acceleration is equal to alpha r, generally not linear, but for this motion, tangential acceleration is equal to linear acceleration. Do not forget that. And from here I can solve for alpha. Alpha will be equal to A over R. And I know A, 0.8 meters per second squared, divided by R, 0.33 meters. And here we're going to find alpha in radian per second squared. Radian appears suddenly as a dial asked me in the classroom. It's because it's not really a unit, it's a value. And as we move from linear to angular variables, that's what we always do. So I actually should have an answer here. Let me not lose time on that. It's been some time already. So alpha is 2.42 rad per second squared from here. So I got alpha second squared from here. Now I can use this equation. Theta is equal to omega 0 times time plus 1 over 2 alpha t squared. Omega 0 is 0. This will cancel, and theta will be equal to 1 over 2 alpha times time squared. 1 over 2. Alpha is 2.42 rad per second squared times the time is 20 seconds. Square of that. Theta should be from here 484 rad. 484 rad. And if you need to know the direction is clockwise, or usually a conventional method of calling clockwise direction negative. So if you see this value as negative, in maybe math and physics they might be doing the same, probably they are doing the same. Don't get confused. The negative direction is clockwise direction in circular motion. So we got theta. I'm going to extend this lecture a little bit more actually and look at on the rest. Let me put this theta value in here. So we know theta now 484 rad. Let me solve also for B and review. We have also C and D. What is the linear distance the axle traveled relative to the ground? We solved a question similar to that. What is the linear distance? One axle is this, so the car traveled simply. Let me call this x. What is x? Traveled in 20 seconds. We solved the fishing rod question. We said how much the length went down, right? The fishing rod was rotating. We found the number of rotations, right? And one rotation takes the unwinds the string about 2 pi r. If we multiply this by the number of rotation, we can find the total length of the string that went down, unwinded. This one can be used here as well. We know theta 484 rad. This is a total angular displacement. Now, one rotation is 2 pi rad, right? If I divide this by 2 pi, as we did in the lecture last time, we can find the number of rotation. I'll call this n rods. It will always be equal to theta over 2 pi. 484 divided by 2 pi. And we'll find the number of rotation from here as 77.03. Simply 77. So now x will be equal to this number of rotation times 2 pi r. Why again? Because in one rotation, x will be 2 pi r. If there's more than one rotation, I multiply by number of rotations to find the total distance. We know r, we know everything, we know number of rotations. We can find the distance traveled in meters. 77.03 times 2 pi is a number and r is 0.33 meters. From here, what we find for x, please check that as well for practice and correct me if I'm wrong, 159.72 meters. Now, there is a very, very good practice you can do in here, and I did it and it works great, that this distance is actually linear distance, x, right? We know from before. We have linear kinematics here. We know A, we know T, we know V0. What we can do is to find x using the linear kinematics equations we know from before. And I want you to try that for practice. I'm going to give you the calculations later on when I post the notes online. You can see it from there. But this same x could be calculated using V0t plus 1 over 2at squared. We know V0 was 0. We know A, linear acceleration, and time. Perfectly foundable from there or from here, and it should give us the correct result if physics works. And physics works. Try it. It might be fun. It really is fun. Let me tell you C as well, and I'll let you go. I'll let you solve C for me. Let me see what the question was asking for C. What is the linear speed of the ground relative speed of the car relative to the ground after 20 seconds, right? So solve x for that, and C, find the linear speed after time passed, 20 seconds. Now, I want you to find this in two ways as well. Use V. Linear speed is equal to tangential speed, right, omega r. You can also use V, final is equal to V initial plus at, and they should give you the same result because they are the same velocity. Linear speed is equal to tangential speed of the tires. It is also equal to using this kinematics equation parts. You may also try, if you want to have more fun, you may also try using final velocity squared is equal to initial squared plus 2ax. Now we also know x from here, right? Or here. all of them should give us the same value or agreeably close values if this logic is all correct. It is correct. It is physics. See you tomorrow.